Assalamualaikum warahmatullahi wabarakatuh. My name is Izzat Ansha bin Latif, and today me and my partner are going to explain the assignment for question 5. So let us do it together. So question 5. Hydrocarbon E has the molecular formula of 112 gram per mole, and then based on the given IR, 1H-NMR, 13C-NMR, 13C-NMR, COSY and HMQC spectra, we will elucidate the structure for the compound E and justify it by tabulating all the information. So first of all, since we have the molecular formula of 112 gram per mole, we can use the rule of 13, where the molecular formula will be divided by 13. So the 112 gram per mole will be divided by 13, and we will get answer of 8.61538. So from this we will get the n and the n is 8. The best formula for this rule of 13 is equal to C and H and plus R. So n is 8, where we get from this, and from the decimal we will the decimal from the answer we will times it with 13, and we will get the R. The R is also 8. So from that information we can calculate the hydrogen deficiency, where n minus R plus 2 and divided by 2. So the n here is 8. 8 divided by 8 minus 8, then plus 2. So 8 minus 8 0, then plus 2 is 2. So 2 will be divided by 2 and equal to 1. So if u equal to 1, then the structure itself will either have one double bond or one ring. So from that we can also conclude that we have 8 carbon and also 16 hydrogens. So that is for the rule of 13. Next we see the IR spectra. So from the IR spectra we can conclude that they are an sp2 found in the structure. sp2, which is a carbon where they have double bond. In the sp2 is at 3090 centimeter per second, and there are also sp3, which is only one single bond at 2995 centimeter per second. And lastly, there are also the carbon-carbon double bond, where is at 1650. All of these are the stretch number for each, which is sp2, so sp2 and here sp3 and here, then alkene, which is carbon-carbon double bond, and these numbers with numbers. So that is all from the IR. Then we continue with the 1H-NMR. The 1H-NMR, first we see at the chemical shift of 0.9, which is here, this one. So it is a doublet. It is a doublet. So then we have at 1.3, which is a quadruplet. As we see here, it's quadruplet. Then at 1.7, as we can see here, is a multiplet. Then At 1.9 or 8, it is a look like a triplet, which is a triplet. Then at here to 2.3 something, which is also a triplet. This one I consider a triplet because we can see here it's kind of there's something up there, which I believe is a peak. And lastly, we can see about around 4.9 and 5.1 singlet at each peak, but I believe that it was a multiplet that can be considered as for the carbon-carbon double bond. So for each chemical shift, there are each assignment, which is 0.9 is CH3 and 1.3 they consist of multiple CH2, and at 1.7 a CH2 they attach to the carbon-carbon double bond, and 1.9 which is CH2 again, and lastly at 4.9 and 5.1 the carbon-carbon double bond. So that is all for the 1H-NMR. And let's see from my part, we're gonna see the 13C NMR. So at the 23 ppm over here, this small one, it was a CH3 peak, the carbon for CH3 peak, and this higher one is at 24 ppm is a CH2 peak, and also at the 29 is also CH2 peak, and at 38 is also CH2 peak. And then we have at 111, it is the carbon they are connected to another carbon through double bond, but this one over here is the carbon that have two hydrogens. And at 148 we have also a carbon that connected to another carbon via double bond, but this one has one hydrogen only. So that is all from me. Thank you.
Hi everyone, today I'll be walking you through a 2D NMR analysis using COSY and HMQC spectra, which are powerful tools for determining the molecular structure. Let's begin with the COSY spectrum. This is a homonuclear correlation chart that shows the proton-proton couplings. Each cross peak in the off-diagonal area tells us that two protons are coupled, meaning that they are close in the structure, typically 2 or 3 bonds apart. So for this spectrum, we can observe that the strong cross peaks between signals in the region of 1 to 2 ppm, which suggests a network of aliphatic protons, likely from methyl or methylene groups. We also see cross peaks near 4.5 to 5 ppm, indicating that these protons are adjacent to electronegative atoms like oxygen and possibly in an ether or ester environment. Now, moving on to the HMQC spectrum. This is a heteronuclear spectrum that connects the proton to the carbon atoms they are directly bonded to. It helps assign which proton signals belongs to which carbon signals. From this plot, we can match the protons at 1 ppm to carbons around 10 to 20 ppm, which are likely methyl groups. Meanwhile, protons at 2 to 3 ppm correlate with carbons between 30 and 50 ppm, indicating methylene or methine groups. And finally, there's a distinct peak pairing protons at 4.5 ppm with carbons at 60 to 70 ppm, which strongly suggests a CH2O linkage consistent with an ether or alcohol. By combining COSY and HMQC, we can piece together how atoms are connected and build up a clearer picture of the molecule's structure. COSY shows which protons are neighbors, while HMQC shows which protons are bonded to which carbons. That's all from me. Thank you. So, to conclude, the structure that we will get is 1 octene.